Okay, so we have to start from diagonalization, right? So last class we had done little eigenvalues and eigenvectors. So we'll start continue with diagonalization. We'll do Fibonacci sequence, and then we'll move to solving problems. Uh, is anyone of you able to share this screen?
Do you want me to
Um,
share a screen?
Let me rejoin. I'm not able to share my screen.
Okay.
Yeah.
Ma'am, you are not audible.
Oh, sorry. I was saying from such a long time. Sorry. I didn't know I was on mute. You are able to see the screen, right?
Yes, ma'am.
Yeah, man.
Okay, okay. Sorry, I was saying, but I think I was on mute. Okay, so what I was saying is like if you have two matrices and you want to check if those two matrices are diagonalizable, okay, so it will happen if you have some invertible matrix. There exists some invertible matrix for which this holds. Your P inverse AP should be B, okay, and saying that A and B are diagonalizable, like they are also in a sense we say they are similar. So similar in a sense, if these two are, if these two matrices will be diagonalizable, there will be many properties that if it holds for one, it will hold for other matrix also. So this is where it's important. This is just a general definition, like what do we mean by two matrices to be diagonalizable. So this is here, B is any general matrix, but we will talk about a special kind of matrix which is a diagonal matrix. And I'm sure. How does a diagonal matrix looks like? So diagonal matrix will be just the elements on the diagonal entries, and rest will be zero, right? So this B we are talking about in general, but let's say if we have a diagonal matrix, okay, and uh, uh, and if we want change color, it's better. Okay. Yeah, so we had talked about like some properties that will be very similar to if the two matrices are diagonalizable. So one can be that their eigenvalues will be similar. If the eigenvalues are similar, we can say their uh, determinant will be same, their traces will be same, and so on. So it simplifies a lot, at least in calculation.
Ma'am, why do you start with P inverse A B
P inverse AB. So
and then you change it to Q inverse B Q?
no, okay. I think I didn't when I was saying it was on mute. So what I said is, we have two matrices A and B, and we want to check, like if we say that these two matrices are diagonalizable, okay,
These two means A and B.
A and B. We are saying A and B will be diagonalizable when if there exists some P, if there exists some P, this P is a matrix, and this it cannot be any general matrix. It should be invertible. Okay. So if this matrix P is invertible, if such matrix exists, such invertible matrix P exists, then it will imply that B equal P inverse AP. This is what it means. And this we have written like for B in the form of A, but we can also write similarly that if there exists some invertible matrix Q, this is also invertible, such that you have A to be some Q inverse BQ. So both way we can write. Okay, so this is what I had written. So either you can write A as Q inverse BQ, or you can write B equal P inverse AP. It just these P and Q should be invertible. All right. Now, yeah, so like let's look at this. Like if I give you any general matrix, if I give you any general matrix A B C D, and if I ask you to find the power of it, it's very difficult, right? If it's just 2 3, then it may be easy, but if I ask you to find the power of 18, it's very difficult to compute. So if in a way we are able to find the matrix similar to this matrix, then it's quite easy to calculate, right? So if we can convert this to a diagonal matrix, and if we have to find the power, this will be same as what we are talking about. Okay. I see. P A P inverse. What did I write? I had written P inverse AP, right? It is right. What are you saying? Wait, it will be P A P inverse. No, this is also right. I mean, it's not an issue. Both are okay. So, like similarly, what we can say is if what we can say is if the matrix A is diagonalizable, if there exists an invertible matrix S such that you can write. So I'm using the notation that is used in the lecture. So this is the diagonal matrix. So this can be written as S inverse AS. Okay, where uh, this is gamma, this is gamma, but this is a notation for diagonal matrix here. So I will not be using this gamma over here. I will mostly use a D. Okay, for this. I'll just write D equal S inverse AS. Okay. So the next thing we have is like if your matrix is diagonalizable, okay, then we say these matrices as n. These matrices will have n linearly in eigenvectors. Okay. So what we say is this is a theorem, and it says we'll prove this in the later part. So it says okay, maybe we'll do it later only. Well, let's see first this. Okay, so we have an n cross n matrix, okay? And for this matrix, for this n cross n matrix, let's say we have n linearly independent eigenvectors. N linearly independent eigenvectors. And these eigenvectors are corresponding to the n distinct eigenvalues. So let's say my eigenvalues are lambda 1, lambda 2 up to lambda n, and I have corresponding to these eigenvalues we have the eigenvectors, which is for lambda 1 we have x1, for lambda 2 we have x2, for up to for lambda n we have xn. Okay, so these are the eigen vectors for the matrix A. So what we are saying is that this P that we saw that we can write D as S inverse AS, right? This is what we have written here. We are saying D equal S inverse AS. So this S or this S is nothing but the eigenvector of the matrix A. Okay. So this S is nothing but it turns out to be the eigenvectors of A, where each of the columns of S are the eigenvectors of A. So I can say that, let's say if x1, x2, xn were the eigenvector, so we have this x1 over here, x2, and it goes on to xn. So let's say this is my S. Now what happened to what happens when you multiply A to this, right? Let's say I multiply A. So what will happen? This A will go inside, right? So ax2, ax1, ax2 up to axn, right? Now, from the eigenvalue definition, you know that your Ax should satisfy lambda x, right? And here, what we have assumed is for each of these lambda i's, we have the eigenvectors as xi. So we have Axi equal lambda I xi, correct? So again, each of these columns we can write it as so ax1 can be written as lambda 1 x1, right? So ax1 will be written as lambda 1 x1, ax2 can be written as lambda 2 x2, correct? So all of these will form the columns of as. So lambda n xn. Now you can write this as, so you can just write this as in this form, which is the product of, so you have eigenvector vectors matrix, you have this s, and all these lambdas, lambda 1 lambda 2 until lambda n goes on the diagonal entry, and all will be 0, right? So if you multiply this is what you get, and this turns out to be what we started with as, right? We started with as and we end up to s time, this is our diagonal matrix t, right? So if you write, you can get d to be s inverse as, and this you can write when, this you can write only when your s is invertible, okay? So if your s was invertible, you can just do s inverse, I mean if s is invertible, s inverse exists, right? So you can multiply s inverse on the both sides, so s inverse as will turn out to be s inverse st, right? And this is nothing but just identity matrix, so your d turns out to be s inverse as. So this is how we get this definition over here, okay? So there are few remarks over here. So the first one is, if you have uh, all the eigenvalues to be distinct, then eigenvectors corresponding to each of the eigenvalues are independent. I think we are doing this proof in week 5, so I will skip it for now. But just keep this in mind. So if you have, let's say, if you have a matrix A, and you have some eigenvalues corresponding to A as A1. So like if A is n cross n, so distinct eigenvalues would be lambda 1, lambda 2 up to lambda n. And each if all of these are distinct, okay, if all are distinct, then we say eigenvectors are independent, all right? And again, the d that we found is not unique, I mean, uh, for different eigenvectors, I mean if you just take the multiple of those eigenvectors, you can get a different d for that. So in a way it is not unique. And also you cannot diagonalize all of the matrices. You cannot, like if I give you any matrix, like let's say, I mean if I give you any matrix of the form a b c d, then we cannot say that all like every time, like all of these matrices will be diagonalizable. It is not possible. I mean sometimes it may not be. So for example, I think you have seen in this lecture also. um, so for example, let's take a to be 0 1 0 0, right? So what is the eigenvalue for this matrix? Can you quickly find it? What is the eigenvalue?
0, ma'am.
Eigenvalue would be 0.
0.
So lambda 1 equal lambda 2 equal 0, right? So what will be the eigenvector?
1 0.
1 0, right? Just give me a minute. Yeah, so the eigenvector is just 1 0. So v1,
Null space of A.
yeah, null space of A. So can you tell me why this matrix cannot be diagonalizable?
It has only one eigenvector.
It has only one eigenvector, right? So yeah, so let's say if we say Okay, like from there it's fine. So it has just eigenvector as 1 0, so this is not diagonalizable. So what would happen if it was diagonalizable? So if it was diagonalizable, I should be able to write this D as P inverse AP, right? If it, let's say if it was diagonalizable, then I should be able to write D as this. Then since my eigenvalues are just 0 0, this D will be just 0 0, right? But my A is not 0 0. I mean, A is not a zero matrix. They are not similar. So it is not diagonalizable. That way also we can argue over here. Then next we have then next what we want to show is, so we want to show that if you have two eigenvalues, let's say if I have a matrix A and I have two eigenvalues corresponding to it, lambda 1, lambda 2, and uh, their corresponding eigenvectors are x1 and x2, where we are saying that lambda 1 is not equal to lambda 2. Then we have to show that x1 x2 is a linearly independent set. So what do you do to check if a set is I mean if a given set is linearly independent? How do you check it?
We have to write that vectors as linear combination, and we have to prove that the scalars are 0.
Zeros, right? So what we can say is, let's say uh, yeah, so we have to basically, like, for any linear combination, so lambda I ai xi, uh, this, if this is 0, if this is 0, then all these ai should be 0. This is what we want to prove. So suppose this is 0, then what happens? Then this is just a1 x1 plus a2 x2 equal to 0. Okay. Now I can also multiply a with this. It won't make a change. So this will be so again, this, since a1 a2 is just a constant, I can pull it out. So in that case, I will just have this a1 ax1 plus sorry uh, plus a2 ax2 equals 0, right? Now ax1 again would be lambda 1 x1. So this would be a1 lambda 1 x1 plus a2 lambda 2 x2. This would be 0. So now I can just take these equations. So let's do this. So you have just a1 x1 plus a2 x2 equal to 0. So what you can do is, you can just multiply this with lambda, let's say lambda 1. Okay. And if you solve for both these equations, what you will get is, uh, you solve, what you will get the first term will cancel out, and then you will have a2 lambda 2 x2 minus lambda 1 a2 x2 equals 0, right? This is what you will get. So you have a2 and
Ma'am, how do you get that one? Well,
which one? This one.
in a step, yeah. Where do you get that one from?
So what I did is, so I had this equation, right? I mean, I got this, and I had assumed that aixi a1 x1 plus a2 x2 is 0. So what I can do is, I can just multiply lambda 1 to this equation, and what I would get, I will get a1 lambda 1 x1 plus a2 lambda 1 x2. Okay. And now I take this equation that we had found, which is a1 lambda 1 x1 plus a2 lambda 2 x2, and make it 0. I mean, we are just solving these two equations now. So you see that if I
How do you get the
subtract
other equation? A to lambda 2 equation, how do you get that one?
this one,
Yeah.
this is just okay. I have a1 x1 plus a2 x2 equals 0. I
Yeah, that's right.
multiplied the matrix A. Okay. Now you see that this a1 and a2 is just a constant. They are constant. So I can pull a1 out, and I will get a1 times ax1 plus a2 times ax2. Correct?
But
And
lambda 1 and lambda 2 are different, is it?
yeah, lambda 1, lambda 2 are different. So lambda 1, lambda 2 are the eigenvalues of A. So you have a matrix A, you have a 2 cross 2 matrix, and the eigenvalues are just lambda 1, lambda 2. And their corresponding eigenvectors I'm saying is x1, x2. So I can write ax1 equal lambda 1 x1 and ax2 equal lambda 2 x2. So this is what I have done over here,
Oh,
right?
this is what you're.
Yeah, so ax1 I am substituting with lambda 1 x1, and ax2 I am substituting with lambda 2 x2,
Okay.
right? Right. The same thing we have done on the top, like when we are proving this part, right? Ax1 we had substituted with lambda 1 x1, lambda 2 x2, and so on. Okay. Then all right. So from there we got that a2 lambda 2 minus lambda 1 x2 should be 0. So we know that lambda 2 lambda 1 are different. So and since they are different and these x2s are non-zero, so my lambda 1 and my lambda 1 is not equal to lambda 2. So this will always I mean they cannot be 0, right? They cannot be 0. uh, and again my x2, this is also non-zero. We have a non, because we have two eigenvalues, so corresponding to we should have two eigenvectors. So this is also non-zero. So what is left is we have a2 equal 0. Now if you substitute, you should also get a1 to be 0. So just substitute in this one and you will get a1 also to be 0. So what we started with that we have a1 x1 plus a2 x2 equals 0, and we wanted to prove, since we wanted to prove that the set x1 x2 are linearly independent, my a1 and a2 should come out to be 0. So this is what we proved. So this shows that my the set x1 x2, which we are calling as the linear the set of eigenvectors of A, they are linearly independent. Okay. So this we can extend to this is just for a matrix of size 2, but if we have to extend it to matrix of size, let's say n, or let's say size k, all right. So let's say size n, let's say we want to do this. So we'll do the same thing. Now we have lambda 1, lambda 2 up to lambda n eigenvalues, and corresponding to each of these eigenvalues we have the eigenvectors, which are x1 x2 up to xn, and all these are distinct eigenvalues. Okay, all these are distinct eigenvalues. Then what we want to prove is this a1 x1 plus a2 x2 plus up to an xn should be 0. Okay. I mean if this is 0, we want to show that all of these ais they should be 0, right? So again we multiply this whole thing with a. Alright, just multiply, and then after this what we will get, we will get a1 a x1 x1 plus up to an a xn to be 0, right?
Yes, ma'am.
Yeah, yeah. So Yeah, so this can be written as ax, so lambda 1 x1 plus up to an lambda n um, xn. This is 0. So let's multiply now again this first equation with lambda 1. Okay, so if I multiply this with lambda 1 and subtract from this equation, we'll get, so let's write it over here first. So you have a1 lambda 1 x1 plus up to an lambda 1 xn equals 0. Okay, so the first term will get cancelled out and we will be left with a2 lambda 2 x2 minus a2 lambda 1 x2 plus it will go on till an lambda n xn minus an lambda 1 xn equals 0. So I can take x2 out here, so even a2 will come out. So a2, you have a2 lambda 2 minus lambda 1 x2 plus up to an lambda n minus lambda 1 xn to be 0. Okay. Then from here we have to show that all these AIs are zeros. Okay, AIs are 0, right? Okay, we'll continue this proof. Just give me some time.
I think we can multiply
Yeah,
initial equation with lambda 2 minus lambda 1.
lambda 2 initial equation. This one,
Yeah,
this one. Or
but
if we
we'll get
do,
a1.
or if we multiply it with lambda 2 minus lambda 1. Okay, then what happens? So you will get lambda 2 a1 lambda 2 minus lambda 1 x1 plus up to an lambda 2 minus lambda 1 xn equals 0. No, but how will you solve this? I mean,
Okay, a2
there's
term will
no.
get cancelled, but we'll get a1. Okay.
Um,
I solved it using induction
we solved it using induction. Okay.
because I stuck at the same point where you stuck. Then
Hmm.
I go back and I solved using induction.
Okay, from induction it's coming out.
Yeah, from induction it
Okay,
went to
okay, okay. Okay,
Sorry, I
let's.
joined in late. Which proof is this, ma'am?
This proof is like when you have a matrix and you have n distinct eigenvalues, then you have to show that this set of distinct eigenvalues, they are linearly independent. This
Okay.
is what we are trying to prove. Okay, just hold on over here. I will come to it at the end and we'll finish it. Okay, let's hold it for some time. Let's keep some space. Okay, I will come over there. So I'll just write down the result first, just for reference. So the result that we were trying to prove is if you have an n cross n matrix and you have n distinct eigenvalues, then eigenvectors corresponding to each of the eigenvalues corresponding to each eigenvalues are linearly independent. Okay, so another question over here. So if you have a matrix A which is 1 4 2 3, you have to check whether it is diagonalizable. So or I think if this is already done in the lecture, right? So you must have done it.
Yes,
So
yes, ma'am.
what about this? If I say is A, which is let's say 0 minus 1 and 1 comma 0, is this diagonalizable? Can you find what is the eigenvalue?
Lambda square is coming out
Plus or minus
uh,
I.
equal to
Yeah, what is coming out? Lambda 1 equal
I, ma'am. Imaginary term.
imaginary number, right? So
yes.
see in
Lambda
such,
square equal to -1.
Okay, okay.
yeah. So such kind of matrices where you will deal with again in week 5. So again it is diagonalizable, but it is not diagonalizable for in the space R. So it will come out to be diagonalizable in the complex space, but it's not diagonalizable in R.
Okay, ma'am.
Yeah. So you can solve. If given any matrix A, you should be able to find. You know how to find your D, right? I mean, you know how to get this D to be S inverse AS. Like if this matrix is given, how do you find this? I mean, how do you find this S? Is the question. You know how to do it?
yeah, we'll put the eigenvectors in it as columns.
Yes.
Yes,
You just
first we
have to
find
add.
eigenvectors.
Eigenvalues first.
Yeah. First, I find the eigenvalues. Then corresponding to those eigenvalues, you find the eigenvectors, and those eigenvectors go in the uh,
Column form.
columns of S. So if it is a 2 cross 2 matrix and it comes out to be actually diagonalizable, so mm, it will have two distinct eigenvectors also. So you'll get some x1 and you'll get x2. So you put it there and just find the inverse that will go over there. And when you do this S inverse A, you should be able to get a diagonal matrix. Okay. Now, okay. So on the same line, like you have also looked at orthogonal matrix, right? We have also talked about orthogonally diagonalizable, right? So when do we say a matrix is orthogonally diagonalizable?
If there exists a orthogonal matrix.
If there exists an orthogonal matrix such that your
S inverse is
Uh,
S transpose.
Eigenvalues are real.
yes, eigenvalue should be real, right? So first of all, what is orthogonal matrix?
The columns of the orthogonal matrix are orthonormal
Yes,
and they are orthogonal to each other.
yeah, and it should satisfy
S
eh,
inverse.
like if I'm saying Q is an orthogonal matrix. Q is an orthogonal matrix. Okay, then my Q transpose Q should be equal to
I
Q transpose, and it should be equal to I. And each of the columns of this matrix should also be should have orthonormal vectors. Each of the columns,
Ma'am.
yeah.
And Q should be a orthonormal matrix, not.
Oh, sorry. When this thing is sorry, each of the columns have uh, a unit length, then it is called orthonormal. Yeah. So write it here. So when each of the columns are unit vectors, then it is orthonormal. Yeah.
Ma'am, actually, I have a doubt. Hello.
Yeah. Yeah. I'm okay. Yeah. Tell me.
Yeah. So basically, if there is a projected matrix, and there is there's a orthonormal vectors that are the vector that is orthonormal to the column space of that. So then the eigenvalues will be how to calculate that? How will we know the eigenvalues?
Uh, okay. If you have a projection matrix, right?
Yeah, like a
Okay.
projected matrix,
Hmm.
and there are the orthonormal vectors that are to the column space of those matrix. So how to find the eigenvalues of those what will be the eigenvalues of those orthonormal vectors?
Eigenvalues of orthonormal vectors.
Oh yeah, which are orthonormal to the column space of the projected matrix.
I think you mean what how to find the eigenvalues for a projection matrix.
Oh yeah, no, no. How to find the eigenvalues for orthonormal vectors of the column
Okay,
space of the projected matrix?
column space of the projected matrix.
Yeah, like
So let's
vectors that
say
are
if we have
orthonormal.
let's say this is column space. Okay, let's say this is my column space. Okay, this some from some matrix, and you're saying if we have some projection on this some projection matrix,
Yes, and
Now,
like vectors that are orthonormal to this projected matrix, what would be the eigenvalues of that?
okay, so you have P, which is okay, and okay, this is projected. This is projection matrix, and you have a matrix, let's say Q, that is uh, wait. Can you repeat again? What is you want this to be?
Ma'am, like I have a
Hmm.
projection matrix,
Hmm.
and then I have a vector that is orthogonal to the column space of that projection matrix.
Vector orthogonal to the column space of projection matrix.
Yeah. So I mean, then what would be the eigenvalue of that? Actually, there is the same question in the graded asked on the same lines. Actually,
Yeah. Let me see the question.
okay.
Yeah. This is week 4, right? Yeah.
Actually, the concept related to that is not clear to me. So
Okay. Let me see what the question is.
I think that's the very first question. So
Can you post it in the screen? Post a screenshot in the chat box. I'll have to
yes,
log in.
yes, ma'am.
Please. Orthogonal to the column space of P.
Okay. If P is a projection matrix, and the eigenvalue corresponding to every non-zero vector orthogonal to the column space of P. Okay. Uh, all right. So, see, the question says you have a projection matrix, okay? And let's say this is any matrix, and you have like uh, whatever the column space it forms, okay? And we are saying some vector is orthogonal to that. All right. So if okay, if some vector is, I can just give a hint because it was, I didn't know it was a credit assignment. So if some vector is orthogonal to the column space, right? So any vector that you take in the column space, that should also be orthogonal to that vector, right?
Yes.
Yeah. So just use these two relations
Ma'am,
and
I
just
didn't
try.
understand it properly actually. Oh,
Okay. So it's more like if you have say some orthogonal, so some this is orthogonal to the column space of A, where this is A just projection matrix, right? Then if you take any vector, let's say in the column space, then that should also be like perpendicular to this B,
yes.
right? Then what will happen? I mean, when are the two vectors perpendicular?
When the dot product is 0.
Dot product is zero, right? So can you try to like just uh, the relation that you have for like ax equal lambda x, where in this
Okay.
case your A is just a projection matrix. Just try to bring it up there and see what it turns up to be. I
Okay,
cannot
ma'am.
tell more because it is no graded solution. Just try to get that into that form, ax equal lambda x, and you should be able to see what should be the eigenvalue in that case.
Okay, ma'am. And for this, we can consider any projection matrix, no?
Yeah, yeah, any in general, any projection matrix.
Okay, ma'am.
Okay, so we'll look at Fibonacci sequence now. So, okay, so this is just one application of this diagonalization, this Fibonacci sequence. Solving this difference equation, second order difference equation, is just an application of diagonalization. That is why we are doing it here, and you will see that this sequence occurs very often in the nature. So it's good to know like some of its properties, you can say. So what is Fibonacci sequence? How does it look like? It's more like of the form like if you add the first term should be 1, the second would be 0, and the third would be sum of these two, right? So it would be 1. Then the fourth should be sum of these two, which is just 2. Then the sum of these two, which is 3. So it will go on, keep on going. But this is the sequence. This is a Fibonacci sequence, and we can write it to whatever extent we want. But like doing it manually, let's say you want a very higher order for like what is, let's say, 100th Fibonacci sequence, then it's difficult to like you cannot sit and count everything and go till 100 and tell, okay, this is my 100th Fibonacci sequence. Okay, or let's say even 100, if it can be done, let's say what about 1000. So it becomes more difficult and difficult to solve such kind of problems. So one solution to this is using the differential equation approach. So uh, we know that we can write this Fibonacci sequence as this difference equation, which looks like something, which looks something like fk plus 2 equal fk plus 1 plus fk. Okay, this is what it looks like, and this is called a difference equation. So do not worry about the terms and all over here. This is a maths topic, so it's okay. And this can be so this is a second order difference equation. All right, this is a second order difference equation, and now we are converting. So it's a property, I mean, any difference equation or any differential equation to say can be converted to a lower order differential equation. So if it's a second order, we can bring it down to a first order differential equation. So that we are doing it. So I will not write the more steps over there, like how is it happening. So bringing it down to the first order, it becomes uk plus 1 to be a uk, where I have taken my uk plus 1 to be fk plus 1 fk. So the second order difference equation, I brought it down to the first order difference equation. Now we want to find the solution for this. What is the solution for this difference equation, right? So it turns out that um this uk equal ak u naught is a solution for is a solution for this uk plus 1 equal a uk. So you can also see that, I mean, I have written uk plus 1 equal a uk. So what will be uk plus 2? Sorry, this was just k. Okay. This was k. So what would be uk plus 1? My uk is fk plus 1 fk. So what will be uk plus 1? What should uk plus 1 be? Anyone?
AK plus 1 U naught.
ak plus 1 u naught. Yeah, that's true. But okay, I was asking in terms of fk. So this is fk plus 2, fk plus 1, right? And now I know that fk plus 2 is nothing but fk plus 1 plus fk, and this is fk plus 1, right? And now we can write this as a matrix A, which looks like this, times fk plus 1 fk, and this is just uk. So what we got is, we got uk plus 1 to be some matrix A times uk. You can see that using this uk equal fk plus 1 fk, we are actually getting uk plus 1 to be a uk, right? So now we want to solve for this difference equation. So how will you go about it? You have the initial solution to be u naught, right? And we know that uk plus 1 equal a uk. So what would u1 be? It will be just a u naught.
Yes.
What would u2 be? It will
It's
be
a
a
square.
u1,
Okay.
and which is a u naught. That is a square u naught, right? You can keep on going, and you will get the general solution that will come out for this difference equation is uk equal a to the power k u naught. So we are saying this is the solution for this difference equation. Now, so what my goal is, like, how do you actually find now this a to the power k, I mean this k. So once you are able to find this k, you will be able to get the uh, your that particular order Fibonacci number. Okay, so this is my goal. We want to find this a to the power k. So Okay. How many of you know how to solve the differential equation? There is a differential equation approach also, but okay, Jivraj, you know. Okay. Sachin. Alright. So, yeah, Sachin, you want to say something? Uh, yeah.
No, ma'am. No.
Okay. Okay. So we can solve it using two different approaches to get a lambda. But using differential equation is a little easy, but uh, if you have not studied before, it may take some time. So just go with the linear algebra, the one which we have seen in the lecture. So okay, now let's say if the solution is this. Now, if this A is diagonalizable, if A is diagonalizable, you will have n independent eigenvectors, right? This we have seen before. If A is diagonalizable, you will have n independent eigenvectors. Now, let's say this set of eigenvectors and this set of n independent eigenvectors are just x1, x2 plus up to xn. Okay. So what will happen? We can, if I take any vector, so if I take u naught, I should be able to write. I should be able to write this as a linear combination of these vectors. So it will give me some c1 x1 plus up to cn xn. And one more thing, that it is not just a set of eigenvectors. It also forms a basis. These set of eigenvectors, if it is if the matrix is diagonalizable, they also form basis. So if I take any vector, uh, I should be able to write it uniquely. Okay. So again, we'll do the same process. We'll multiply this with a, and I'll just skip the steps here, and I can write it as c1 lambda 1 x1 plus up to cn lambda n xn, right? And if I want to find a square u naught, a square u naught, so again it would be just of the form c1 lambda 1 square x1 plus up to c2 lambda to square x2 plus up to cn lambda n square x2. So this is how it will look like. So any general equation, like for any uk, basically, so uk, which is nothing but a to the power k u naught, right? This is a to the power k u naught. So if I just extend this, I can write this solution, so remember, this solution is the solution for this difference equation, which is uk plus 1 equal auk. And this we have reduced it from our Fibonacci sequence, that difference version, which was fk plus 2 equal fk plus 1 plus fk. So this, it turns out that this solution uk for this equation is nothing but c1 lambda 1 to the power k x1 plus up to Cn lambda n to the power k xn. So this is our UK. This is the solution. So we are interested in finding the solution for this equation. Okay. Now, how do you find these lambdas? How do you find these lambda? What was A? What was our A?
1110.
1110, right? This was our A. And these, what is the lambda that will come out to be? So I will just I'll finally write the answer. I'll skip this step. So your lambdas will come out to be 1 plus minus root 5 by 2. This is the lambda that will come out to be. And this value that you're seeing here is also called the golden ratio in Fibonacci sequence. This is called golden ratio. Maybe you can read about it if you're interested. So this number is also called the golden ratio. And
So golden ratio is the eigenvalue.
yes, eigenvalues. Now, okay, since this is just a 2 cross 2 matrix, how will the solution looks like? This solution will look like UK to be C1 lambda 1 um, lambda 1 square x1 uh,
It's a ma'am
okay,
U1.
sorry, you this is okay.
U1.
Yeah, I have found the eigenvalues for this matrix A. Okay, so my u0 was what? My u0 was c1 x1 plus c2 x2.
Which is equal to 1 comma 0.
Okay.
Because you know it is f1 comma f0.
So what you can do? You can also find the. So these are the eigenvalues, right? Just also go ahead and find the. Um,
Eigenvector ma'am.
yes, eigenvectors. So what is eigenvector that you get? As we solved it.
Ma'am, x1 is equal to lambda 1 1 and x2 is equal to lambda 2 2. Sorry, 1.
Yeah, tell me.
X1 is equal to lambda 1 1.
Lambda 1 1. What do you mean by lambda 1 1?
1 plus 5, root 5 by 2 is lambda.
Okay, final. Okay.
1 plus root 5 by 2.
Comma and 1.
And 1.
Okay.
Okay.
Okay. So this is the eigenvector that you get. And what is the other one that you get?
With minus sign in between 1 plus under root 5.
1 minus root
Okay. Yeah.
5 by
Okay. 1
2.
minus root 5 by 2 and
1.
just 1. Okay. So okay. So the final answer that we are interested in is this. So using this, you can also solve for this C1 and C2 because my U0 is just what it is F1 and F0, right? And what is F1? F1 is just 1 and F0 is just
0.
0, right? and this should be equal to this c1 time x1 that you have found plus this c2 times x2 that you have found, right? So if you just compute it, you will get this c1 and c2. Okay.
Yes, ma'am.
So I think it comes out to be uh,
C1 is equal to 1 upon
1
root
by root
5
5 and turns out to be minus 1 by
minus 1 upon root 5.
root 5. So this is the general solution that you get for this system of equation. So this is a general solution that you get when c1 x1 plus c2 x2. Now, okay, so what we said is my UK uh, will look something like c1 lambda 1 to the power k x1 plus c2 lambda 2 to the power k x2. This is how it looks like, and this uk is nothing but just fk plus 1 fk, right? And we have already found our c1, we already know lambda 1, we have my x1, so just compute, write it over there. Okay. And in general, it turns out that my fk is 1 by root 5 1 plus root 5 by 2 to the power k. The other term we like just skip because it turns out like as k keeps on increasing, that value is very small, so we can ignore that. So the other term that we will get is something of 1 minus root 5 by 2 to the power k form.
Yes,
And
ma'am.
what will happen is whenever this k is very large, this value decreases. I mean, this value keeps on decreasing, so we can ignore for larger values, we can ignore, and we'll just stick to this one. So this is my kth Fibonacci number that we get. So it may not be possible that this number is will be an integer that you will look like. If you're talking about a Fibonacci number, you will think that this should be an integer, right? But it is possible that if you solve it, it may not come out to be integer. So you take any whatever value you get, you take the nearest integer to it, and that you will call it as your that kth or whatever nth Fibonacci number. Okay. So whenever you have to find any Fibonacci number in a sequence, you can just use this. Just compute k whatever you want, and that would be your answer.
Ma'am,
And take it to the nearest integer.
if k is small, then we have to include this other term also, right? 1
Yeah,
minus
if
root
k,
5.
k is small, you should add the other term also. But how small? Um, um, Not sure how small you can consider. Maybe like at what term it should be very less. So maybe you can just cross check, like substitute few values and see for at what k you are getting actually this value to be very less. So from there we can ignore. But generally, if k is small, you need not even go through this formula. I mean, you can easily find it out, no? You using this counting. If this k is small, so only if the k is very large, we use this. Okay. Okay. So that yeah, for k equal 10, it would be 0.007. Okay. Yeah, that's quite less. I mean, yeah, you can just check because till again till 10 it's much easier to calculate using counting. So I'll stop sharing this and I'll present the slides.
So, ma'am, if I want to refer to any differential equations notes, so where should I go and do that?
Differential equation notes. There are many books you can find. I think it's just a general idea about it. You can find it even online
Okay.
if you just need the introduction. Yeah. If you want to study in detail, then you may need a book, or you can just go through some YouTube videos. So the idea there is quite interesting. Like you have a differential equation, and when you look at that differential equation, your exponential e to the power, like let's say e to the power lambda t, turns out to be a very um, obvious answer that solves the differential equation. And uh, that I mean, and that function like that, and if we call that e to the power lambda t as, let's say if we call it as eigenfunction, then what is it doing is it's taking any like any vector or anything, and it's returning uh, like that vector times e to the power lambda t. So it looks very similar to your eigenvector concept. So yeah, if you are interested in OD, you can just look at it. Then you can look at the different approach also in that case.
Okay. Okay.
Yeah. Is my screen still visible? Oh, wait, let me rejoin again. I am still again facing problem in sharing. Oh, sorry, I was not audible. Okay. Yeah, I was asking when do we say a matrix to be a singular matrix?
And the determinant is 0.
Yeah.
Matrix inverse is not possible.
Yeah, when it is not invertible, or also when determinant is uh, 0. So for what value of x you are getting the determinant to be 0?
Ma'am, it's x is equal to 4.
Um, x equal 4. It will be t equal to inverse anything. Okay. Yeah, for x equal 4, you will get uh, this determine in the matrix to be singular. So I hope that is clear to everyone. Yeah. Okay. So you have the matrix 1022, and the eigenvectors of this matrix is written in the form of 1 comma a and 1 comma b. So what would be a plus b? Question. Okay, point 0.5. Okay. Is everyone getting 0.5 as the answer? All of you got 0.5 as the answer? Anyone? I saw only one answer. No, just you know how to solve for eigenvector, right?
And the eigenvalues are 1 and 2.
Ma'am, can we solve this question? Is it feasible?
Yeah. Yeah, you can solve this question. So you have this matrix 1, 2, 0, 2. So I get the eigenvalues. So I do 1 minus lambda, 2 minus lambda, 2, 0. I just get 1 minus lambda, 2 minus lambda equals 0. Right? And this is what? This is 2 minus lambda minus 2 lambda plus lambda square equals 0. And this is lambda square minus 3 lambda plus 2 equal 0. So if you solve for this, you will get lambda to be 1 and lambda to be 2. Now what happens for lambda equal 1? So you will have 1 minus 1 which is 0. You have 2, and 2 minus 1 which is 1. So I will have x1, x2, right? And this is 2x2 equals 0, and this is x2 equals 0, right? So the eigenvector should be, so the eigenvector corresponding
1,
to
0.
lambda equal 1 would be just 1 comma 0. Yeah. Now same you do for lambda equal 2. So what would happen? In that case, you have 1 minus lambda which is 1 minus 2 which is minus 1, and 2, and 0, 0, and this is x1, x2 is 0. So you will get minus x1 plus 2x2 equals 0. So basically you're getting x1 to be 2x2. So I can write the eigenvector v to be, if I take this to be 1, it should be 1 by 2. So why I have written in like 1b, like 1 and 1 by 2 form? Because see, in the questions given, the eigenvectors are written in the form 1a and 1b. So I have tried to bring it to the same uh, format. So let's say if I call this v1 to be 1a, and if I call this v2 to be 1b, then what is your a and what is your b? A
A
is
will be
0
0.
and b would be 0.5. So a plus b is just 0.5. Okay, I hope it is clear. All right, let's do the next one. You have the matrix 3 5 4 5 and x 3 by 5. So if this matrix is orthogonal, then what should be the value of x? Minus 4 by 5.
minus 4 by 11.
Minus 4 by 5. So all of you got minus 4 by 5? Yeah. So how do you find it?
The dot product of the column should be 0.
The dot product of the column should be 0. Yeah. So you just get, uh, you will get x equal minus 4.5. Okay. So I'll move to the next one now.
Ma'am, can I get a
Sorry, your voice is
can I
breaking.
get a detailed solution for these questions? Is it available somewhere?
Detailed solution. I'm not
Actually, I'm
sure.
finding this a bit difficult to solve, like the eigenvalues and vectors. So I
Okay.
wanted to see the steps also, actually.
Okay. So if you have the problem, so I think for first, I will just write the answer if I have not written it. But I can just write the answer and share. When I upload the slide, I will write the answer and upload.
Okay, okay.
Yeah. And for practice, I had referred to like practice some problems also. It would be good
Okay.
apart from these. Y equal 10, x equal 4, plus y equal 14. Yeah. So you are getting y equal 10 and x equal 4. Right?
Yes, ma'am.
Hmm. But I think it's x equal not 4, it should be minus 4.
X plus y is equal to 6, man.
Yeah, x plus 5 would be 6 and not 14. Yeah, that's what. I'll just write the answer for this also.
X will be minus 4, y will be 10.
Yeah. So we are just using like this is a matrix and the eigenvalues are 4 and 8, and we can just use the property. So use determinant of A is product of eigenvalues and trace of A to be sum of the eigenvalues lambda 1 plus lambda 2. Okay, so the eigenvalues are given to be 4 and 8, so it should be just 32, and the trace would be 12. And determinant of A would be 2y minus 3x, and trace of A would be 2 plus 5, 2 plus y. Just solve these two and you will get x to be minus 4, y to be 10. So x plus 5 would be 6.
Ma'am,
Yeah.
I also use a minus lambda method to find x and y.
Okay. Yeah, that is also fine. I think it will take a little more time, I guess, but that is also fine.
Yes, ma'am.
Yeah. So if you
So,
know the determinant and trace, it's just product and sum of the eigenvalues, then it's quite easy. Okay.
So where are these slides uploaded, ma'am? Or where can
Uh,
I access them?
yeah, so it will be uploaded on the portal under the live session section. So
Okay.
you go to supplementary content, there will be a separate section called live session. So there it should be there tomorrow. 2 to the power 9. Okay. Anyone else? Same answer. Okay. So is it clear to all of you why is it 2 to the power 9? Yes, it is using diagonalization. Yes. Yes, Prashant. So what is the first eigenvalue you got?
2 to the power of 9.
Yeah, I mean, what is the eigenvalue for A?
Root 2 and minus square root of 2.
Yeah, root 2 to the power 18 and minus root 2 to the power 18. So both will be 2 to the power 9, right? So you'll have two eigenvalues and both will be 2 to the power 9,
Oh, okay, because
right?
18 is even.
Yes. Okay. So is it clear to all of you? Just write down the answer here. So the eigenvalues for A, values for A comes out to be plus minus under root 2. So eigenvalues for, so if I'm able to write A to be P D P inverse, so my eigenvalues for D uh, would be just 2 to the power 9, which is, can just calculate. Okay. You have two matrices here and you have to check which of them cannot be diagonalized. Okay. So yes, first one is not diagonalizable and the second one is diagonalizable. So it's clear for all of you?
Ma'am, it is
Sorry.
because the number of eigenvectors are one.
Yeah, right.
Less.
And you have just you don't have distinct eigenvalues in the first case. You just have 0, 0 eigenvalues, and you're just getting one eigenvector. So yes, it is not diagonalizable because you just have one eigenvector. But in the second case, you will have two different eigenvalues and you'll get two different eigenvectors, and hence it's diagonalizable. What about this one?
A is 3 cross 3, ma'am.
A is a 3 cross 3 matrix. So
A is not diagonalizable.
Uh, Option 2, ma'am.
A is not diagonalizable, right? Do A is A invertible?
No, ma'am.
Right? Okay. So if you just have the eigenvectors as multiple of 100, um, will it have a repeated eigenvalue?
No, ma'am, not necessary.
Uh, yeah.
Ma'am, can
Okay.
you explain this? I didn't understand the options.
So you have a matrix, right? You have a 3 cross 3 matrix, and we are saying for that matrix we have the eigenvectors which are just a multiple of 100. Okay. I mean, let's say if my one eigenvector is 100, the other would be 200, then it would be 300, and so on. Okay, so some multiple of 100. So we have seen before, like before this, we saw that if you have uh, if you have just one eigenvector, I mean, uh, then in that case, like if you have a repeated eigenvalue, and for that you are just like the previous example, for say you had two eigenvalues which are 0, 0, but you were just getting one eigenvector 10, which, I mean, it can be written as c0, right? So it didn't turn out to be the diagonalizable. We had looked at the property 2. Yeah.
Ma'am, previous example at 0, it is not repeated. It is repeated or
Previous,
not repeated?
the first one, it is repeated, right?
Okay, 0 is repeated.
Yeah. What did you get for the first part?
0.
0,
No,
right? 0,
lambda
0.
square equal to 0. So
Yeah.
can we say 0 is repeated?
Yeah, we can.
Oh, okay, because the power is 2.
Yeah.
And how to know if it has a repeated eigenvalue? Oh,
How to know
I
if
think
it
that
has a repeated eigenvalue?
I think
Uh,
that is
s-
also an option.
uh, yeah, it is an option. Yeah, I think so. So, okay, we had seen some example, no? Wait. Like for example, wait, let me see. I think we did some example. Like yeah, the first example, very first example that we saw there also, you had I mean in this case also we are getting lambda to be 0 0. I mean you have the same eigenvalue. When do you call an eigenvalue to be repeated? When you have one eigenvalue that is coming more than once, any eigenvalue coming more than once, then such kind of in that cases we say this matrix has a repeated eigenvalue.
The arithmetic multiplicity is more than
uh,
one.
yeah, arithmetic multiplicity is more than one, yeah, but the eigenvector that you found is just one.
Ma'am, here the
Ma'am, my
geometric
question is
multiplicity
that
will be 1 and arithmetic multiplicity will be 2.
Will be
Right?
two. Yeah, yeah, yeah.
ma'am, my question is like given a eigenvector, how will we know whether it is a repeated vector eigenvalue or no?
No, I mean, there in the question, it is like you have the eigenvalues. Sorry, we have the eigenvector, but they are multiple of this vector. So, let's say if this is my eigenvector 1 0 0, right? So, whatever the eigenvectors are, just multiple of this. So, in this case, like similar cases we saw in this example where we had a repeated eigenvalue, right?
Ma'am, what is the arithmetic and geometric multiplicity?
Arithmetic and geometric multiplicity. Okay. So arithmetic multiplicity is like this. You can write like for example, I was let's say lambda square equals 0. Okay. So you will get what? You will get lambda 1. I mean, you know that there are two lambdas here, right? I mean, two lambdas you will get, and both is taking the value 0.
Yes.
Yeah. So both lambda 1 and lambda 2 are 0 here. Now for eigenvector, what do you need? You need ax to be lambda x, right? So this basically the space. If you find this eigenvector, you will get to be let's say it is some 1 1. Okay. And what is the dimension of this eigenvector? Like it's just one eigenvector uh, that is spanning your whole eigenspace. You have just one eigenvector spanning a two-dimensional space, right? So in this case, geometric multiplicity is 1.
How can lambda be 1 1?
How can lambda be? Sorry, not lambda. Mistake. This is b. I'm talking about b.
X. Yeah.
So, basically, in general, what you can look at is what is the null space of this a minus lambda I, right? So this null space of a minus lambda I will give you the geometric multiplicity. And null space in this case, if the vector is, if eigenvector is just 1, 1, then null space is just span of this vector 1, 1, and it is just dimension is just 1, right? And algebraic multiplicity is like how many times an eigenvalue is repeating. That is the algebraic multiplicity. So whenever these two are not same, whenever your algebraic multiplicity and geometric multiplicity are not same, uh, we say the matrix is not diagonalizable. So even in one of the TA session, I guess I'm not sure if it has been already done or it will be like it will be done. So if you want, you can ask, maybe if you need more, like solve some more problems on diagonalize, like some matrices to be some diagonalizable matrices, then we can just like in one of the TA session we can ask to do just uh, some problems on this portion, this topic. Is that okay? And if we are doing the problem, we'll record those sessions and maybe we can put it on the portal itself, or let's put the slides, anything, right?
Okay, ma'am.
Yeah.
Example, ma'am.
Sorry, example, I didn't
No,
hear.
TA session for what?
TA session for more examples, more problems, practice.
Okay.
Okay, so these were the only questions I had for today. So if the solution is not written, I will upload it. I'll add the solutions and upload it, and you can find it on the live session section.
Okay, ma'am.
Yeah. Okay, so how are the